Okay, so shall we start? Okay, so last time I was telling about operator state correspondence, and we were drawing such a picture of the complex sphere cut into pieces, and we had some local fields placed in some points. So there was 0, z1, and so on, the n, and there was some infinity. So we found that a correct way to send the operator to infinity is to multiply it by r r to delta, or delta of r, and then send its position to infinity. And so the equality we had was that the correlator O O delta 0 of 0 and so on, O delta infinity of infinity equals to some state which is created at infinity times O n minus 1 of O n of z times the n times O 1 of z1 delta 0. So we wrote this equality, but here it was assumed from the very beginning that if there is such a picture, then absolute value of z1 is less than absolute value of z2, and so on. And these operators act by one by one, because it's just a rule of composition of different parts in which we cut our sphere. But these are just complex numbers, and we can consider, for example, analytic continuation of this object in this complex numbers. And if you move, for example, so it is somewhere z2. And if you move z2 closer to 0 and perform this procedure again, so there's such a picture, and there is another picture where first z1 and z2 are indistinguishable, they have the same absolute value of z, and then it can switch to a picture when z2 is inside and z1 is outside. We see this correspondence between path integral and the operator formalism tells us that the object which should be written on the right hand side for any positions of these should be not just this product. It should be a radially ordered product. Which means that R of A of Z, B of W equals to A of Z, B of W if absolute value of W is less than absolute value of Z, less or equal, and B of W, A of Z when absolute value of Z is less or equal than absolute value of W. And actually, we worked only with bosonic fields, but in principle, we could have Grassmann variables in the path integral. And in this case, we have to write -1 to, I don't know how to denote this parity, but let us write it like this. So it is a parity of A times parity of B. And actually, so you see this radial order can be defined in two different ways when absolute value of z equals to absolute value of W, and this trick can be used to compute commutators of some operators, because mm, mm, because one function can be computed in kind of in different ways. Okay, can be expanded in different ways. So. So and now we want to ask what is the evolution operator in this case. So originally, if you work with the usual QFT, when time direction is just one of the coordinates, then we can say that Hamiltonian operator corresponding to this evolution is just T00. So let me check that coordinate is on. But this is the operator which generates a T translation. So in this case, it's natural to find some operator which corresponds to dilatation. So it should correspond to this vector field z dz, and we know that this vector field corresponds to L0. But But let us try to be more precise. Let us try to write some identity between this L0 and vertex operators. So first, let us say who is this L0. And to do this, we can first introduce the action of energy momentum tensor on the space of on the Hilbert space of theory. Because now a Hilbert space is a space of functions on a circle. So we can say that this energy momentum tensor has a Laurent expansion. And this Laurent expansion will be defined on some circle of radius r. One. So the value of z equals to r. So it is so we actually take it as a definition. Some operators ln over z n plus 2. So this ln's act on this Hilbert space of theory. And now let us see what is this action. So, for example, let us consider the action of T of z on the vacuum from so in principle it equals to some ln over z n plus 2 acting on vacuum. But we know that this operator is regular when z goes to 0. So on the left-hand side, we can say that it is just so we can send z to infinity, and now this energy momentum tensor will stand precisely at the origin. And by the operator state correspondence, we can say that, for example, if we put here t of 0, it will create a state uh, mm, of this kind. So the operator t of 0 at the origin plus sum from k equals to 1 to infinity z to the k over k factorial. And here we will have a case like decay t of 0. So now we compare this with the right hand side. So it is z minus 2 L0 acting on a vacuum plus z minus 1 L minus 1 acting on the vacuum plus L minus 2 acting on the vacuum plus some like zk L minus 2 minus k acting on the vacuum. And comparing these two fields, we can see that L0 acting on the vacuum is 0. L minus 1 is 0 as well. And then, in general, L minus 2 acting on the vacuum is a state generated by the energy momentum tensor. And L minus k minus 2 is 1 over k factorial, like dk t of 0. So are there any questions? So it is one example of the action of the Virasoro algebra. And then we can, of course, add more energy momentum tensors. They will act somehow on this state. Mm-hmm. And because 0 is not a special point, it's just some random point on a complex sphere, and there is no operators in this point, so this correlator cannot have singularities. So if for any yes. So So it is one example of the action. And so we also know that all this L in K is greater than or equal to 0 acting on vacuum, it gives 0. Uh, so I don't want to study this example in details now. The only thing we need to remember that energy momentum tensor is L minus 2 acting in a vacuum. So we will return to this later. So at the moment, I want to find. Actually, you can also check the action on state delta zero. So another example, T of z acting on delta zero, and well, let me write. Let me suppose that it is written under some correlator. T of that, O delta zero of zero, it equals to all this times T of zero times delta zero. And from the left-hand side, we know the OP of energy momentum tensor with a field of dimension delta, with primary field of dimension delta. It equals to delta 0 over z squared plus something else. And so from this we conclude that it equals to L0 over z squared times delta 0. So coefficient in front of z squared is this one. So we conclude that under this state delta 0 is the eigenstate of L0 with the eigenvalue delta 0. Like this. So now let us compute commutation relation of this lens with primary fields. So to do this, we need to remember this radial ordering prescription. Because what we want to compute is the following. We want to compute Ln with O delta O delta at point Z. So this operator O delta of point Z acts between the Hilbert space on a little bit smaller radius to the Hilbert space on a little bit bigger radius. So we can write this commutator as a difference. So first it equals to a difference ln O delta of Z minus O delta of Z Ln. And then it can be written as the following radial orderings. So in the first integral, we should say that the absolute value of W is greater than absolute value of Z. And then multiply W n plus 1 dW T of W O delta of Z. And in the other integral, we can write almost the same, but with different radial ordering, with absolute value of W less than absolute value of Z. Wn plus 1 dW T of W O delta of Z. So now in these formulas, no, maybe it's better to put heads on these operators, because here it means that they are not just local observables, they are operators acting on the Hilbert space. And which Hilbert space? It is defined by the absolute value of W and of Z. So are there any questions about this formula? Yes, so once we have this, we can write that it equals the we can draw this two contours. So this is point Z, and first contour goes here, second contour goes in the opposite direction here. So it's just one integral in the counterclockwise direction around Z. So it equals to the integral of, again, a radially ordered expression, integral around Z. Wn plus 1 dW T of W O delta of Z. And at this moment we can say that this radially ordered product of operators is the expression which we get from the path integral, which does not care about this radial quantization and does not know who is time, who is space, and it just knows that such a product of two operators has a Laurent expansion in W minus Z. And if this O delta is a primary field, we know how this expansion looks like. Namely, we can write two singular terms of this expansion, which are the essential ones. Equals to W to n plus Wn plus 1 dW O delta of W over Z minus W squared plus dO delta of W or Z minus W plus something regular, which does not appear in the answer. And once we compute, I missed delta here. Once we compute this, we get n plus 1 W to n plus 1 delta W to n O delta of W plus plus Wn plus 1 d delta of d O delta of W. Sorry, not of. Yes, sorry, I missed the two variables. Here's W minus Z, so expansion is around Z. Z to the n, Z, and here Z. So we get this equality that maybe let me write it here. Commutator of ln with O delta of Z equals to n plus 1 delta Zn O delta of Z plus Zn plus 1 dz O delta of Z. It's actually very important equality, and we'll understand this later. But so it allows us to pull any combination of the Virasoro generators through the primary field. So and express correlators of representation of lns through the correlator without them. But for now, I would like to use this identity for a kind of practical purpose. So, are there any questions about this? Okay, so I want to use this identity for L0. So, namely, so for L0, this is that the commutator of L0 with this O delta of Z equals to uh, to delta delta O delta of Z plus Z dz. And we can use this formula as as an operator differential equation for O delta. So it follows from here that O delta of Z equals to what? To Z to minus delta Z to L0 O delta of 1 Z to minus L0, yeah, and that's all. So, is it fine? So the point is that this formula is a result of Heisenberg evolution of the operator O delta of 1. So this is Heisenberg evolution. And L0 is the Hamiltonian. So we can now try to rewrite this this partition function using such a representation of our operators. And so Yes. So, mm, so you see, this evolution in the ideal coordinate contains some extra shifts related to dimension of the operator. For example, here we have this z plus 2 in this expansion. So it's a natural combination. Uh, we can also say something like that this evolution in the coordinate log of z will be just an ordinary evolution. So, and if you consider um, the object like dz to power delta times O delta of z, mm, it will equal to d log of z to power delta e to the L0 log of z or delta of 1 e to minus L0 log of z. So the meaning of this is that in principle a sphere without zero and infinity is the same as cylinder, and this mapping can be done precisely by log of the transformation. But if you live on a cylinder, then all slices of this cylinder are equivalent because so it's a log of the coordinate. So all the slices are equivalent, and so we don't see this z explicitly. But if we work on a sphere, we can have there is a radius of a circle, and it can appear somewhere in some simple way, like z to delta. Is it fine? Mm. So now uh, about this partition function. So uh, what did I want to say? Yeah, so we can write it as this delta infinity. Mm. So let us insert this representation of all these operators in in this form. So we will have z to minus delta n uh, zn to L0 on delta n of 1 z n over zn minus 1 no, zn minus L0 and so on. Oh, I also forgot to add z n minus 1 to minus delta n minus 1 and so on, and finally all z 1 to minus delta 1 all delta 1 of 1 times z1 to minus L0 acting on acting on delta 0. So we have some formula of this kind, and this one. Yes. Delta n zn. So. In the second bracket. The first C. The first C. Sorry. Yes. Thanks. So we can write a formula of this kind. And what we see that there are some operators which are the same everywhere. So they differ only by this scaling factor, and there are insertions of these ratios z over z to power minus L0. And, so it means that parallel we can identify, so we can identify insertion of such annulus of like this is z, this is like insertion of such an annulus should be identified when the operator lambda to L0. And this is like um, Schrödinger representation for the quantum mechanical evolution. We have some operators, we have some operator which does not depend on z, and it is interlaced with the evolution operators. So mm, and also uh, mm, there was a computation for a spherical correlation function, but people also study correlation functions on a torus or on higher genus surfaces. So, what is the correct object on a torus, for example? Uh, so here we have just put some state at the infinity, but we could also mm, close it with like mm, here we had delta infinity something delta zero as matrix element, and but here we can consider a trace of q to power L0 times product of all these operators. So if we decide to work with mm, with a toric coordinate, which is log z, let us call it t. And then it will equal to q to L0 t to t e to the L0 minus L0 tn minus 1 or delta n minus 1 of 1 and so on, O delta 1 of 1 times e to minus t1 . So here we have this picture which goes to infinity. Here we have t1 and so on, tn, and in the toric case this picture is closed. So there is maybe better to draw it like this. and so this is 0. This is mm, log of q, and we need to glue this right side of a torus to the left side. So this evolution now does not go to infinity, but closes this way. So, uh, so I've inserted here another evolution operator.
Yeah, but I'm saying, so I start with the picture above, in which I have this correlation function, and now I have to do delta infinity and delta zero to be the same state, and then sum over all possible deltas. Now, like I C1 and Cn, they cancel, right? Because they are the same state, right?
No, you're right. So there is a point, there is some point 0, which corresponds to mm, how to say it. If
But then, sorry, it should be the delta n, delta y, delta n minus 1 in the trace.
here, um, because I missed that operator. Yes, it's in the storm. 12.0.10. So the point is that overall overall time translation equals to logarithm of q, because this operators of conjugation appear as operator and operator inverse. So they just move all these O's from point 0 to some other point. And mm, so we can imagine this picture like everything is this evolution is split into such parts from T1 to T2, from T2 to T3, and so on. And the last step of evolution is the evolution from Tn to T1, but on this cycle of torus. Uh, so I've just said that I want to consider such such an expression, product of these operators times q to power L0. So I can write that q is some e to well e to minus big T. So we found here, looking at these pictures, that insertion of the operator lambda to L0 corresponds to evolution from a circle lambda 0 to a circle lambda. And here we try to do the same. We try to close this. We try to. If you work in a spherical coordinate, we can think about this like this. We cut some circle inside, cut some circle outside, and identify them. And this.
This partition function, like what we call the partition function on the top, there is still the points, the coordinates of the points related to the dimension or not?
No, because I've switched to cylindrical coordinates in this way.
So this got eaten by the differentials.
Yes, and this is a correlator of this operators on a cylinder.
Also because it will be translationally valid.
Yes, so it will be translationally covariant. We will need to keep these factors z to power delta, but they are very easy to trace. So and welcome. And the limiting behavior is that I can write it as maybe not q to L0, but e to trace of e2 minus t times L0. When we send t to infinity, we see that this operator turns into a projector on the lowest state, and in the sense, we come back to sphere. So our torus becomes infinitely long, and the only state which survives is some vacuum. It depends on which precise space we take here. But in any case, it will be some kind of the lowest state, which survives in this limit, times e to minus dimension of the state. So is it fine or not? Yeah. So what we know at the moment, we know that there is some conformal field theory, and the algebra of operators of this theory contains Virasoro algebra, and sometimes it can contain some other simpler algebras or more complicated algebras, depending on the case. And on this algebras act both on the Hilbert space of theory and on the space of operators of this theory. And we also know that space of operators and the Hilbert space and the space of states are the same. And correspondence is so intuitively, this correspondence can be understood like this. If you put some operator at the origin, it means that we create a state corresponding to this operator. And or vice versa. We can take some state at the origin and imagine that it is placed in some other point, and it will correspond to some non-trivial operator. And here, for example, we saw an example of this correspondence, that there is this vacuum module of the Virasoro algebra, and L minus 2 state corresponds to the energy momentum tensor. But let us study this in more detail. So we saw the commutation relation in the Virasoro algebra, and so let me remind this. Okay, so probably I can start raising this. And in the other example, in the free boson case, we had another algebra. So these algebras are infinite dimensional, and as a consequence of this, their representations will be very big, and and they act on the on any space which is present in the conformal field theory. So it is a very natural idea now to find the decomposition of these Hilbert spaces into a sum of well, in some senses, in some cases reducible, in some cases non-reducible representations of such conformal algebras. So in arbitrary conformal field theory, we can only find representations of the Virasoro algebra, but in some cases they can have extra structure. And it's basically the main reason why 2D CFT is so successful. Because of this big conformal algebra, we can organize many things in a much more convenient way, combining all the representations of Rasura into a kind of a single blocks. And now I want to tell something about these representations. So mm, So as a warm-up example, we can consider the representation theory of the Heisenberg algebra. So although it's a warm-up example, it appears everywhere in conformal field theory. So in some sense, any representation of the Virasoro is somehow similar to a representation of this Heisenberg. Uh, so, so what we have here, it's just a combination of Heisenberg. So it's a combination of harmonic oscillators formed by n and a minus n, plus a zero mode for n equals to 0, which is important. So I have that if n is greater than 0, then it is an annihilation operator, and it it will annihilate the state. So, sorry. So there exists vacuum labeled by some alpha such that a greater than 0 acting on this vacuum gives 0, and a0 acts with alpha. So, so it's obvious, right? That there is such a vector. If you are interested in unitary representations, at least. And all other states are generated by creation operators. So H alpha is span of A minus N1, A minus Nk, acting on alpha. When so is it better to write this to say that N1 is greater or equal than N2, greater or equal than Nk, greater than 0, right? So there is actually a relation between trivial commutation relation between these algebras, which I wrote at some moment, and it tells us that Ln with a k is equal to minus k a k plus n. So if you act with L0 on the state, so L0 commuting with L minus k equals to k, a minus k, right? So the question is, what is the eigenvalue? How does L0 act on such state? Mm-hmm. Plus actually delta alpha, which we can either compute from scratch, or just say that it is alpha squared over 2, but minus n1 a minus nk acting on alpha, right? So in the eigenstate, and since this space is infinite dimensional, people always like to represent such spaces as infinite direct sums of subspaces with a fixed eigenvalue of L0. So we can say that H alpha is a sum from from which from n greater from n equals to 0 to infinity of H alpha n. The now there is a question. What are the dimensions of these spaces? Right? Yes. So for examples of these spaces. H alpha 0 is just a vacuum. H alpha 1 is a span of a minus 1 vacuum. H alpha 2 is a span of a minus 2 vacuum, a minus 1 squared vacuum, and so on. In principle, we can just say that yes, it's partition number. It's a number of ways to decompose an integer number as a sum of ordered integer numbers. So here we see 1, 1, 2, then there will be 3, and then I don't remember precisely. But if we want, so let me check my recording. If we want to work with such dimensions, it is always convenient to consider not such formulas like this one, but their generating functions, characters. And so if you see this character, I understand why it is useful. So, namely, it's better to consider a trace of Q to L0 over the space H H alpha, and it is easy to compute because it is Q to alpha squared over 2. The contribution coming from the vacuum state, and now it's a product of traces. Maybe traces over spaces which are polynomials of minus case generator. And here we take only this part of L0 corresponding to this particular generator from k equals to 0 to infinity. And each of these traces, they equal to 1 plus q to power k plus q to power 2k plus and so on. This is because we can take arbitrary power of this a minus k. And if we sum all this, we get q to alpha squared over 2 times product from k equals to 1 to infinity, 1 over 1 minus q to the power k. This is called character. And is it clear to everyone that if we then start decomposing this function as a series in Q, it will give precisely this expression, that it will be Q to alpha squared over 2 sum of P of n Q to the n. So is it clear, or it's better to try to prove it somehow? Or what do you think? So there is also a combinatorial picture describing such ordered tuples of numbers. They are precisely Young diagrams. So um, this expression corresponds to the Young diagram with the first row of length n1, second row of length n2, and n3, and so on, some nk. Right? And mm, so this labeling means that each row corresponds to some creation operator, and the number of rows of given length equals to the number of such creation operators. It's one way to label the subjects, and another way is just to say, this is when we fix the number of boxes in this Young diagram. If we don't care about the number of boxes, we can perform this computation of a character. And when we do this, we only care about the number of creation operators with the index k, which appear in the state. And we take some over all possibilities here. Then another creation operator with different numbers completely independent from this one, and we can also compute. We can also compute this contributions with the appropriate weight. So so we have infinite number of geometric percussions, and finally we have this infinite product. So, but if we don't know about this oscillators, we can think about this in a combinatorial way. So this sum of p of n q to the power n equals to what? It equals to 1 plus q squared plus q third plus and so on. 1 plus q squared plus q squared squared plus q squared cubed plus and so on. And so on. And now we open these brackets, and we can identify such ways to open these brackets with partitions of the number n. So, namely, if we take this term, q cubed times q squared square, it means that we get q third times q squared and plus some plus other terms, and this term should be identified with the following the following partition. It is 1 plus 1 plus 1, because this bracket is responsible for a number of occurrences of 1, and this bracket is responsible for a number of occurrences of 2, and so this is plus 2 plus 2. And the overall degree counting parameter precisely counts for us the total number. So if you open all these brackets, all terms in the answer will be in one-to-one correspondence with different ways to represent number n as an integer partition. So it's fine, right? Yeah. So, but and also we can see from this formula and compare it with this one that this character of the representation is very similar to a torus partition function. It's actually is a piece of vacuum partition function, like partition function of theory without any operators. And it is also natural to expect that since a torus is a torus and it should not know about this quantization, so we can look at it in two different ways. One way is to actually in infinitely many different ways. So one way to look at it is to say that Hilbert spaces correspond to this slices. This is the original quantization in which we obtained in this picture. But another way is, of course, to say that a Hilbert space is correspond to these slices. So we can cut it in some different way. And we can also place them in some other way. So there is entire modular group acting on a torus, and it maps all these different ways to choose a quantization. But since all the subjects describe the same theory, and they should come from the path integral in some way. It is natural to expect that partition functions of this theory will, so in the best case, they will be modularly invariant, and or if not, we can expect at least some good modular properties. And it's actually the case, because we see that if we consider a Q to 1 over 24 of the product of 1 minus Q to the power K, so it will be the Dedekind eta function. Which is modularly invariant with, well, in this case, with, I think, weight 1 or 1/2. I forgot, actually. Maybe weight. Yeah, maybe weight 1/2. So, yeah, but here we looked at the representation of this free boson of the Heisenberg, and in our theory, we saw this entire set of vertex operators with real alphas. Because if you consider something with a complex alpha, it will correspond to non-normalizable state, so we don't want to include them. And we can say that entire Hilbert space of free boson maybe somewhere else. So this entire Hilbert space will be the direct sum over all alphas. Alpha is real H alpha tensor H bar alpha, because there is anti-homomorphic algebra acting there. So we should also add this. And since the exponential operator is a product of two operators with the same alpha, homomorphic one and anti-homomorphic one, we will have this expression. uh, it's direct integral, but well, uh, what is the difference between them? And, ah, mhm. So sometimes the summation is uh, the summation corresponds to summation of all possible values of center of mass momentum of this free field. So, and mm, uh, there are theories where we have an infinite number of such modules, but there are of course cases when we have only a few of them. Uh, so uh, now let us say something about the Virasoro algebra. So we see here we had a relation that L0 with a minus n equals to n a minus n. And so, and what can we see for the Virasoro? We see that there is the same relation of 0 with L minus 1 with L minus n equals to n L minus n. Uh, it follows from the commutation relations. And we also see that these commutation relations allow us to reorder any numbers of L's in such a way that highest L stays at the left and the lowest L stays on the right. So the only question is if such states are linearly independent, but we will study this later. In general position, the states are linearly independent. So we will compute a bilinear form of such states and see this. But for now, we can just say that any state can be brought to this form. So, in general position, this Hilbert space will be L minus n1, L minus nk, acting on delta. And this delta is defined by the property that L0 acting on delta is delta Lk is greater than 0. They act by 0. So so it's the same as for the for this oscillator. We see from this relation that L's with negative indices increase the eigenvalue of OZR, and L's with positive indices decrease it. And it is a very natural assumption for the CFT that there are no operators with arbitrarily low negative dimensions. So it means that there there should exist such a vector which is cued by all positive L's at some moment, because we don't have a states with a lower dimension. And one way to understand why such states are prohibited is to compute the scalar product of two such states. So, namely, let us compute a square of a state O minus 1 delta. It equals to a state sitting at infinity, L1, L minus 1 delta squared. And now we can swap this L1 and L minus 1 using commutation relation. It will be to be 2L0 plus L minus 1 L1. So let me think. No, I'm actually trying to prove that there are no primary fields with negative dimension if our theory is unitary. So for the primary field, it equals to delta scalar product of delta times delta. And if we have a non-primary field, or maybe the simplest argument is that if we have fields with negative dimensions, non-primary fields, then their correlators will grow with distance, and we say that this is non-physical, and we don't want to consider them. But actually, this is only if we work with the actual physical CFT, because if we just study representation theory, we can consider modules of Versor algebra which do not have such a structure. Because, for example, we can consider a highest vector, which is the eigenvector of L1. or joint eigenvector of L1 and L2. And just say that this does not appear in physical systems.
Why is the case that the adjoint of L of minus n is L of n? Why the adjoint of L of minus n is L of n?
Because let us look at the energy momentum tensor. So maybe T of z and dz squared. This is ln over the n plus 1 or n plus 2 dz squared. This is expansion around 0 in the local coordinate z equals to 0. If we now want to expand this around infinity, we can write this as a sum of L minus n d 1 over 1 over z to the power n plus 2 d 1 over z power 2. So the point is that expansion of the energy momentum tensor around so in local coordinate around 0 contains this lns, and expansion in the same local coordinate around infinity, which is 1 over that, contains L minus n's. So the action on that other point is given by L minus n's. So is it fine?
So the requirement of self-adjointness of T implies this, the fact that L of n and L of minus n are one disjoint of the other.
Yes.
Because like
So
inversion is like taking the adjoint operator on the graph, basically.
yes. So, here we don't have complex conjugation, just this said. I don't know what is the correct name for this, but it is uh, just a bilinear form on this representation. It's not linear, anti-linear. So there is no complex conjugation anywhere. It's,
But I can think of when I act on the left, I can think of acting with the adjoint operator.
a joint kind of transposed.
Once I have a binary form, I can speak about adjoints.
Mm-hmm.
So
Yes. So this bilinear form is complex linear in both argument, because it computes so this bilinear form on the space of this kind of h h times h to complex numbers, and it computes correlators of like O infinity times O0. So yes, it's just bilinear form without any complex conjugations, and yes, we can take conjugate operator to to the one acting here. So.
But I'm not completely sure that O infinity lies in the same, brow infinity lies in the same age as O0. Because we have the inversion of coordinates to bring in on the left side.
We know that they are abstractly the same space, in the space of operators. So.
Sure, but there is. But I'm saying that, like we identify O like h of 0, like with h of infinity up to multiplying by z to the delta, something like this, no?
But deltas are the same here and there. So.
Yeah, no, I mean, I don't think that's not my point. My point is that if I want to do to consider brass or the dual of H, uh, there is some involution in the middle. It's not a complex conjugation, but there is some involution that brings me to the dual.
No, I think it should be just z to 1 over z, because, for example, let us consider.
Yes, that's exactly the involution I'm speaking about.
Mhm.
Yeah,
Yes.
indeed.
So if you insert here the energy momentum tensor T of z somewhere, then T of z dz squared dz squared, then this will be the same as this correlator O0 with the same operator but placed so this is of infinity, this is of 0. O0 of infinity times a t of 1 over z times O infinity of 0 d 1 over z squared, right?
True that H1 and swap prime cats.
Mm,
I mean, because T of
I
Z,
think yes.
no, I mean, T of Z, this square, and T of 1 over Z, D of 1 over Z square is the same thing.
Mm,
Because it's a tensor, no? So, like, I don't see why we should swap the prime cats.
no, but it's computed in a different point. So we took this correlator and just performed the uh, oh, we took this correlator and performed the change of coordinates.
Yes.
Right.
But the coordinates are, I mean, you just change the coordinate of T. You,
Mm.
you don't
And
T in another,
and swapped. Let me better use a of 0, b of infinity, two different operators. B of 0, a of infinity.
sorry, can you explain why you swap prime cats?
Because so maybe uh, mm, I want to say that if we define the action of t on the states at 0, it will be obtained. So it will be equivalent to the action of L minus n's on states at infinity.
That I agree.
Mm-hmm.
But then it would.
So this is precisely why I wanted to do this, because here we can send z to infinity. So on the left hand side we can send z to infinity and see the action on b when it is placed at infinity, and on the right hand side we can send when we do this, this t goes to 0 and acts on this b. So it's a kind of identity that b L minus n a is the same as uh, a L n b.
So that's how you.
So I'm in this way I'm proving that L minus n a is a L n conjugated. Maybe like this.
Okay, because so for you this like this product, this linear form is real.
Yes, complex.
Yeah, no, but I mean
Mhm.
is linear in both entries.
Yes, yes.
Because otherwise there could be some complex conjugation in what you're writing, right?
Yes.
Okay.
And it would be horrible because it is a quite natural assumption that complex conjugate of t is t bar, and we don't have the linear form between ln and ln bar. They just commute.
Mm-hmm.
They're different algebras. So.
But this is okay. But if we compare this to standard quantum mechanics, like there I mean, this would be a nice quantum mechanical system in the end, of course. I mean, so and there usually the product is taken to be linear in one side and then anti-linear in the other. So how do the two things see?
Let me think. Also, this bilinear form is called, I don't remember, Schrader or Stravelter, a Schrader bilinear form, and it is always defined in QFT, because any QFT has a two-point function, and we can consider this two-point function as a bilinear form on the space of operators.
So you're saying that to define the usual scalar product, I need to add another involution or something like this?
Let me think.
Yeah, yeah,
Hmm? Uh, mm,
to satisfy certain properties that reflect the positivity of the scalar product.
yes, precisely. Yes. So the scalar product should be positive. So, and, mm, so concern quantum mechanics. I don't know. So if we just if you want to consider one-dimensional quantum mechanics, Can we have any analog of this operator states correspondence? I think no, because mm,
Well, I mean, I can always think like operators creating states, right?
mm, for example, for harmonic oscillator, we would need um, oh, so
But it's what we were saying last time, right? Define the interspace to the
so
create the
yes, but in the case of quantum mechanics, we can oh, actually we can choose both possibilities because this system is itself combination of a big number of harmonic oscillators, and we can choose this bilinear forms for each of them, and each of them is positive. Mm. So.
because I think is what is saying that there is some other map, and with this other map we define the alpha scalar product in the interspace.
Mm. So actually, if we want to consider the true CFT, we should always add complex conjugate modules. Uh,
Okay, but those in some sense are chiral, right? They don't speak to each other. They are
yes.
just basically two copies of the same system decoupled in some sense.
Yes. Mm,
This I don't think solves really the problem.
yes, but if you have a product H times H bar, we can construct this half linear term which would multiply H with a complex conjugate of H bar, like, but I'm not sure that it is a good object to consider.
I mean, also because like since we are just considering the holomorphic part, is because in general we don't have like they should be kind of orthogonal somehow to two spaces or not.
Mm. What do you mean by orthogonal?
Like if I take the scalar product of delta and delta bar,
Uh, no, there is not no such thing. There is a vacuum vector which is a delta tensor, a delta bar,
indeed that's
and
what I'm trying to say. That delta scalar delta bar is zero. Like when I take scalar products, I have the holomorphic part with itself and the anti-holomorphic part with.
oh, but they're just in different spaces. We don't need to, so it's not a direct sum of homomorphic and anti-homomorphic. It's a tensor product.
Yeah,
The,
yes. That's what I'm trying to say. That uh, if you okay, you cannot take scalar products, or I mean, if you want to define, they should be zero according to this picture because they belong to different spaces.
well, you can define it, but you will never need to compute such a scalar product.
Yes. So why aren't you saying that before?
Mm, no, before I tried to say that we can try to define a scalar product on a scalar product by taking conjugate of each of the states, like it will be uh, uh, somehow cost a scalar product, but maybe it's a stupid idea. Mm, so, but this scalar product should also be, so if you try to define a scalar product to be this halfway bilinear, it probably will become positive defined by construction, I think. Maybe not necessary. But this one should be positive from a kind of physical arguments because we know that this bilinear form on the space of fields can be diagonalized, and if you put the same field at 0 and at infinity, or maybe better to say that we move 0 and infinity quite close to each other, then a correlator of more or less the square of this field should be some positive number. Mm. Oh, of course, if you work with fermions, it's not so easy to say this. But in any case, we assume that if it is some CFT, then the scalar product should be non-degenerate. And maybe that's all for today. So, yeah, thanks for your attention. So next time I will tell about the structure of the Verma modules, about free boson realization of this representation, because they act on the same space.